now we want to describe this two-particle system. We will see that even if the system is not made up of only two particles, but the particles are contained in the nucleus and we only have one electron here, then the behavior is very similar. We will see that. But for now, I'm considering a two-particle system, and this is like the hydrogen atom, right? So where this is the electron, and this is the proton. Now, I want to write down the expression for the kinetic energy. This is important because it will appear in the Hamiltonian. So the Hamiltonian operator will be the kinetic energy of the first particle, which is P1 squared over 2m1, and P1 here is an operator. Okay, remember that the operator for momentum is, so if you want I can put a hat here, but doesn't really matter. It's just minus I h bar, the gradient. Okay, so if you want, I mean, this is a vector and this is also a vector. The gradient is a vector. And maybe I could put a subscript here 1 because this gradient is to be performed, is to be let's say computed with respect to the coordinates of the first particle, whereas the momentum of the second particle is to be computed with respect to the coordinates of the second particle. And of course here we have P2 squared divided by 2m2, just like this. Okay, now let's reason classically first. I will not consider these expressions here at the moment. Okay, but as you can see, I mean, if we write it, if we write the expression like this for the system, it is kind of complicated because we have to consider gradients with respect to the coordinates of one particle and a gradient with respect to the coordinates of the second particle. We would like to do something simpler than that. Okay, but in order to simplify this expression, we need to do some manipulation. Okay, some just algebraic manipulation. It's not very complicated. Now let's reason classically. What do we know classically? We know that the momentum of the first particle is equal to the mass of the first particle times the velocity of the first particle. Okay? Instead of using vectors here or arrows, I'm using just these bars, these straight bars, to simplify my handwriting. But this means that I'm considering vectors. Okay? And of course, the same holds for P2. P2 will be equal to M2 times V2. And we also know that we have, in general, in a system made up of two particles, we can calculate a center of mass, where the center of mass is defined like this. So the vector OG, let's say, so I'm assuming now that I have some origin. Let's assume that here I have an origin of a reference frame, and I'm observing from this reference frame here. Now, this is the origin of the reference frame, and for example, to denote the position of the particle M1, of the particle 1, characterized by the mass M1, let's say that this point here is P1. So the position of the first particle would be OP1, whereas the position of the second particle there will be OP2. OP1 is the position of the first particle, OP2 is the position of the second particle, which is this vector here. It's a position vector. Whereas the position of the center of mass, let's assume that this center of mass is here. Well, this can be calculating like this. It's M1 OP1 plus M2 OP2 divided by the total mass of the system, which is M1 plus M2. It's a simple formula. If you want, we can rewrite it like this. It's M1 OP1 plus M2 OP2 equal to M1 plus M2 times OG. Now I would like to take the derivative of this expression here with respect to time. I want to take the derivative with respect to time, because this way, if I take the derivative, for example, of OP1 with respect to time, I will get the velocity of the first particle, which is v1. By definition, when I take the derivative of a position vector, I will take the velocity. I will obtain the velocity. And the same for OP2, and something similar for OG. So here, when I take the derivative of OG, I will get the velocity of the center of mass, yes. And here I have m1 v1 plus m2 v2 equal to m1 plus m2 times the velocity of g. Okay, so now I can also rewrite it like this. So if I take these quantities over to the left hand side, I will be able to rewrite it like this: m1 v1 minus vg plus m2 v2 minus vg equal to 0. Now, this quantity here, it is the velocity of the first particle, from which I have to subtract the velocity of the center of mass. So it means that this is the velocity of the first particle with respect to the center of mass. So I can label it like this. It is v1g, and this is, if you want, v2g. Okay, so this simply means that, for example, if I choose this point O coincident with the center of mass, of course I will have that m1 and v1 plus m2 v2 will be equal to 0, just like this expression tells me. Okay, so instead of writing v1g and v2g, in the following I will just write v1 and v2. So I will assume that my point O will be coincident with the point G, with the center of mass. From here I have m1 v1 plus m2 v2 equal to 0. And this is just p1, whereas this is just p2. So from here I simply get that p1 is equal to minus p2. Okay, and now I can substitute this relation in the relation for the kinetic energy, which is p1 squared over 2m1 plus p2 squared over 2m2. And now I can substitute p2 equal to p1, so I can rewrite it as p1 squared over 2, 1 over m1 plus 1 over m2. And this can be written like this: it's p1 squared over 2 m1 m2 divided by m1 plus m2. And this quantity here in the denominator has a name. It's an important quantity. This is usually called mu, and this mu here is the reduced mass of the system. Let me write it down. It's the reduced mass of the system. So, or maybe instead of reduced, also equivalent mass. Because if you take a look at how the expression is written down there, so p1 squared is also equal to p2 squared, if you want, p2 squared over 2 mu, okay, where mu as units of mass, and this quantity here is just like the kinetic energy of a single particle whose mass is equal to mu. So it's the equivalent mass of the system, let's say. It's an equivalent mass of a one particle system. You can think of it that way. And therefore, now we have simplified our expression. And let me say something more on this constant mu here. This constant mu, which is equal to m1, m2 divided by m1 plus m2. Now let's substitute the mass of the electron with the mass of the proton. Now let's assume that M2 is the electron, so it's Me if you want. It's the mass of the electron, whereas M1 is the mass of the proton. But the mass of the proton is approximately 1,836 times the mass of the electron, so it's very large with respect to the mass of the electron. And therefore, it means that this is approximately equal to the mass of the electron here, because in the denominator, M1 is much larger than M2, and therefore M1 divided by M1 is approximately 1, okay? So M1 divided by M1 plus M2 is approximately 1, and therefore here we have M2. M2 is equal to Me. So we see that this equivalent mass is approximately equal to the mass of the electron, okay? And this basically means, if you also take a look at the expression for the center of gravity, the center of mass here, this basically means that OG is approximately coincident with OP1. So the center of mass is approximately here, where the first particle is located, okay? And that's just one proton. Now imagine if the nucleus of the atom, of the ion, if you want, contains more particles. Well, it means that this approximation is even better, okay? So now what we can do is essentially consider this to be the the energy of the system. It's the energy of the electron, because the nucleus is I mean, if we think of that classically, it is there, it is fixed, it's not moving, because it's the electron that's moving in the outer shell, and this is important to understand. And if we generalize it to quantum mechanics, we just have to replace the operator for the gradient, I mean here, for the electron. So this will be just some minus I h bar del, where in this case this del here is the distance. So we have to consider the operator where we have a particle here, which is the electron, M2. We have an origin, which is located at the center of the nucleus, and then uh, our coordinates are simply measured from this point here, and that's it. So it's pretty straightforward in this case. Okay, so the expression for the Hamiltonian will simplify a lot, because we will have some p squared. Now I will drop this this subscript 2 here. I will just call it p squared divided by 2 mu, and then I will have some potential. Okay, so the kinetic energy is of course equal to p squared divided by 2m, but in the expression for the Hamiltonian, I also have to consider a potential. So here, I will also have to put a potential energy, which will depend on the distance between the two particles. So I can also call it r here, which is a function of the coordinates x, y, z. Of course, it's the square root of x squared plus y squared plus z squared, but um, I will just write it like this: v of r plus v of r. Okay, and this v of r is related to the Coulomb force. Now we will make this assumption. We will assume that the interaction will be similar to a Coulomb attraction, where I have essentially I have a product of the charges of the charge of the electron, which is minus e. Okay, where I consider e to be positive, so I will put a minus sign here because the electron is negatively charged. And then I will have the charge of the nucleus, which is it is plus z times e, where I'm assuming now that I have some protons in the nucleus and I have no electrons there, and this z here is the atomic number. So for example, for the hydrogen atom, it will be equal to 1. Okay, so that's it. And then I will have to divide by r. So the energy is minus z e squared divided by r, the potential energy. And the potential energy, as you can see, is negative in this case because we are considering attraction. There is an attraction because the particles have opposite charges. Okay, so this is the expression for the potential. And we will go further from here next time.